Physics 1 about oscillations. So we aim to compare predicted motion of a mass suspended by a spring simulated in a computational model to the observed motion of that mass on a spring. We also aim to plot the energy changes that occur in the system for predicted motion. Changes in gravitational potential, kinetic, and spring potential energy will be accounted for. We will use tracker analysis and glow script for the computational and theoretical models respectively. So the Newton's second law and the force of gravity are the principles that will be used in modeling for this experiment. The energy principle also will be used, and that says that the change in energy of the system, delta E, equals 0, and that is also equal to the change in internal energy plus the change in work done by the surroundings on the system. Not change in work, just work done by the surroundings on the system. So, so the types of energy that the system can have are translational kinetic energy, gravitational potential energy, spring potential energy, and spring potential energy. Those are the kinds that we'll be using in this lab. There are others, but they're not relevant. So this is the free body diagram that illustrates the system we have. The system is the Earth, the spring, the mass, and we put nothing in the surroundings, which means that the work done by the surroundings is 0 because there's nothing doing work. So these are the data and measurements from tracker that we found. As you can see, the x position versus time graphs and y position versus time graphs is over here. And yeah, we can see that they're approximately sinusoidal and cosinusoidal. And so yeah, those are the graphs. So the initial calculations were done with Newton's second law and the energy principle. The spring constant was also calculated to be the mass over the square of the ratio between the period of oscillations and 2 pi. The simulation parameters for the code were given by Hooke's law and as well as Newton's second law as well as the energy principle. So the computational model is shown here. As you can see, we have the comparison between the empirical models and the experimental models to the right. There's a slight phase shift in both of the models. There's an amplitude difference in the comparison between x position and y and time, and there's a difference there's like a shift up. There's like a vertical shift in the difference between y position over time, but the amplitude is like pretty close. But there's a phase shift in both. So the change in gravitational potential energy and spring potential energy oscillate inversely. The change in kinetic energy also oscillates, but it's of smaller magnitude and it has a phase shift. The change in energy is constant and always 0, which represents the idea that energy is conserved in accordance with the energy principle. The empirical model shows, we already discussed the differences between the empirical models and the theoretical model. This difference represents some oversights, probably due to the potential sources of error that we have, which are that the spring was assumed to be massless, the drag force was not accounted for, losses due to vibrational, rotational, and thermal energy were also not accounted for. There's also inherent inconsistency with identification of the center of mass through the tracker analysis. So there are some further questions that we have, which are that the energy principle is satisfied? The answer is yes. Summing up the changes in internal energy, kinetic energy gives us a total of 0. And the change in internal energy is the sum of the change in gravitational and spring potential energies. And those are the red and green lines. And so summing those up and then also summing that up with the change in kinetic energy, which is that blue line that we see here, that gives us 0, which is a change in total energy, which the energy principle states should be 0. Therefore, we comply with the energy principle. So the period of oscillations with the x and y positions over time is slightly different, which is not expected. The difference is about 0.19 seconds, and it impacts the calculation of the spring constant k. It can be accounted for likely due to the drag force and the assumption that the spring is massless.